Calculation of round foundation slabs subjected to non-uniform base deformation under complex loads. Authors: Radomir Timchenko, Dmitry Krishko, Sergii Holovko, Oleksii Holovko, Oleksandr Samorodov. Slab foundations occupy a significant place among building structures and are widely used in industrial and civil construction. Monolithic reinforced concrete slab foundations of rectangular, polygonal, and round shape are used in construction on natural foundations. They are particularly widely used in complex engineering and geological conditions in the construction of high-rise buildings of various functional purposes, as well as industrial structures such as silos, elevators, flue pipes, etc. The joint operation of these structures with the ground base is conditioned by many factors that should be taken into account when laying foundations, increasing load during construction of buildings and structures, and by deformation influences from the base during the operation period. Thus, the technical and economic parameters of slab foundations can be determined taking into account their actual operation under real operating conditions, such as loading modes, the nature of force and deformation effects, peculiarities of development of irreversible deformations, settlement of structures, the sequence of formation, opening and closing of cracks, etc. At present, modern calculation methods for buildings and structures operating in complex soil conditions, and, first of all, foundation structures interacting with unevenly deformed base are being developed. Theoretical development and experimental substantiation of nonlinear models of the soil environment, which allow describing the process of its deformation at all stages of loading, are highlighted by I.P. Boyko, E.F. Vinokurov, U.L. Vinikov, A.L. Golden, A.E. Delnik, B.I. Diduk, U.K. Zaretsky, N.L. Zutsenko, Z.G. Termartorosian, D.M. Shapiro, V.G. Shapoval, V.B. Shvets, V.N. A.U. Bishop, D. Drucker, Schofield and others have made a significant contribution to the development of the theory of calculation and the practice of foundation construction for special construction conditions. U.M. Abelev, A.L. Gottman, Z. Gottman, B.I. Dalmatov, U.K. Zaretsky, S.N. Klepikov, A.A. Petrikov, E.A. Sorokin, R.O. Timchenko, A.B. Fadiv, A.V. Shkola, J. Gedz, E. Kviatek, G. Kratch, U. Lutkins. The research aims to substantiate and develop a method of calculating round foundation slabs interacting with the non-uniformly deformed base, taking into account inelastic deformations of reinforced concrete and soil under complex loading. In order to achieve this goal, it is necessary to solve the following tasks. To perform an analysis of the available experimental data and theoretical generalizations to select the regularity of deformation of the reinforced concrete slab and the soil base under complex loading. To carry out complex experimental and theoretical studies of the stress-deformed state of round-shaped plates in their joint work with the deformable base. To develop static methods of calculating round foundation slabs with comprehensive consideration of nonlinear and inelastic deformations of reinforced concrete and soil under complex load. To develop application programs to calculate round foundation slabs in a nonlinear and non-elastic arrangement. To identify features and patterns of nonlinear inelastic deformation of round foundation slabs and bases by simulating their work using the developed methods and calculation programs. To introduce the research results into design practice, construction and operation of buildings and structures operating under special conditions. Round foundation slabs are calculated for difficult soil conditions taking into account the infinite stiffness of the slabs. Design and construction practice indicates that, on the one hand, with high slab stiffness there are significant strength reserves, the use of which is hindered by the lack of uniform recommendations for rational slab foundation design. On the other hand, even with sufficient stiffness, the foundation slab bends and gets maximum deflection under load, especially in the nonlinear stage of reinforced concrete work, when cracks and fracture lines are formed. It follows that the assumption of infinite stiffness does not reflect the actual work of the structure, and deformation, flexibility, of the slab should be considered in the calculation. Consideration of nonlinear deformation of materials that causes stress redistribution in both components of the foundation-based system makes the contact problem under conditions of non-uniform deformation of the foundation nonlinear not only physically but also geometrically, because the locations of the base detachment from the foundation bed are unknown in advance. The calculation of slab foundations with respect to the action of non-uniform deformations of the foundations is performed by considering all possible deformations from the state of the foundation-based joint work, taking into account the most unfavorable combination of the effects. The most unfavorable options for reactive pressures to be implemented can occur with the following deformation force combinations. Figure 1. Curvature of the convex surface of the base and the external moment which is perpendicular to the curvature plane. Curvature of the concave surface of the base and the external moment which is parallel to the curvature plane. A ledge or failure at the end of the base and the external moment which is perpendicular to the ledge line. There is only one-way connection between the foundation slab and the base, i.e. the base is not capable of preventing the separation of the foundation from the soil, but only prevents the penetration of the slab. Further deformation of the base changes physical and mechanical characteristics of the soil, the bearing capacity and the stiffness of the base are reduced. At the same time, the soil deformation curve in the new state do not coincide with the first curve. Therefore, when solving the contact problem for these conditions, it is necessary to take into account the differences in the soil load curves for different points before and after the weakening of the base. Solving the problem of determining the load-bearing capacity of foundation slabs operating under non-uniform base deformations requires considering nonlinear and inelastic deformations of reinforced concrete and soil. In addition, it is necessary to take into account geometric nonlinearity of the contact problem. The operation of round foundation slabs under non-uniform deformations of the base, taking into account deformation characteristics of reinforced concrete and soil, can be studied on mathematical models. For this purpose, consider a round foundation slab under the influence of arbitrary normal to the median plane of the slab external load intensity Q, R, phi, and lying on the soil base, characterized by the stiffness coefficient K1, R, phi, figure 2, where R, phi are polar coordinates. The slab has a finite stiffness, but large enough to ignore membrane forces acting on the foundation bed and having little effect on the overall slab operation, especially on its load-bearing capacity. The load from these forces is perceived only by the lower part of the cross-section, so they cannot exhaust the load-bearing capacity of the slab. The behavior of a reinforced concrete foundation slab at any operation stage is described by systems of resolving equations, combining equilibrium, geometric and physical equations ones. The calculation is made under various deformation conditions of the round foundation slab base with the following characteristics. Geometric dimensions of the slab are shown in figure 3a. Curves of the coefficients of reinforcement of the lower and upper slab zones in the radial and annular directions are shown in figure 3b. Concrete is class C25/30, as working reinforcement is represented by class A400 steel, radial rods are A400 empty set 28, ring rods are A400 empty set 25. Consider first the operation of the foundation slab under normal soil conditions with the increased total vertical load F caused by the structure. For calculation, the soil deformation diagram is taken and the initial stiffness coefficient of the base is Ki equals 58.8 mn/m3. The simulation results, settling W, reactive pressures P, radial and annular moments Mr and M phi, crack formation zones, at load F equal to 200 mn, 300 mn, 375 mn, and 400 mn are shown in figure 4. At F equals 400 mn, plastic hinges form closed areas, annular and radial fracture lines divide the slab into several separate parts, and thus the load-bearing capacity of the foundation slab is exhausted. The value F U equals 400 mn is the limit load on a given slab under normal soil conditions. Simulation of the curvature of the convex base surface. Now consider the behavior of the round foundation slab with the curvature of the convex surface of the base along the axis upsilon, i.e. upsilon, r, phi, equals upsilon, x, figure 5. The characteristics of the slab are the same. It is subject to a total vertical load F. 1 is equal to 200 mn, which is twice as less than the limit load F. U, nr equals F. U slash F. 1 is equal to 2, 0 is the factor of safety of the foundation slab under normal soil conditions. It is necessary to determine the stress-deformed state of the round foundation slab when the curvature of the convex base surface is increased. The following values of the curvature radius Rz are used in simulation: 10,000 m, 6,000 m, 4,000 m. Diagrams of the calculated values are shown in Figure 5 and Figure 6, and in Figure 7 shows the process of developing cracks and fracture lines on it and the lower surfaces of the slab when increasing the curvature of the convex base surface. With the curvature radius Rz, U1 equals 4,000 m, it is impossible to further increase the effect on the foundation because at the footing support along the y-axis, the points of maximum values of the soil reactive forces and fracture lines are formed and develop, dividing the slab into independent parts. Thus, the load-bearing capacity of the foundation slab is exhausted. Similar simulation is performed with the value of the total vertical load F. 2 is equal to 300 mn and the following values of the convex curvature radius Rz, 15,000 m, 12,000 m, and 9,000 m. The load-bearing capacity of the slab is exhausted with the curvature radius Rz, U2 equals 9,000 m. The simulation results, design values, development of cracks and fracture lines, are shown in Figure 8, Figure 9, Figure 10. Simulation with the curvature of the concave base surface. With the same slab characteristics and total vertical loads F. 1 is equal to 200 mn and F. 2 is equal to 300 mn, it is necessary to determine the stress-deformed state of the foundation slab by increasing the curvature of the concave base surface along the y-axis, i.e. upsilon, r, phi, equals upsilon, x, Figure 11, Figure 12, Figure 13. The following values of the conventional curvature radii of the concave base surface Rz are simulated: 10,000 m, 6,000 m, 5,000 m at load F. 1, 15,000 m, 12,000 m, 10,000 m at load F. 2. Reduced characteristics of the deformed base are determined according. In the first case, i.e. at F. 1, the load-bearing capacity of the structure is exhausted at the value Rz, U1 equals 5,000 m, and in the second case, for F. 2, at Rz, U2 equals 10,000 m. The simulation results are shown in Figure 14, Figure 15, Figure 16. Simulation with the base settling at the end of the foundation. It is necessary to investigate the behavior of the round foundation slab with different values of the settling section of the base at the end of the foundation. The slab undergoes the following loads: the total vertical load F. equals 200 mn, the external moment M1 equals 150 mnm. The height of the center of gravity of the structure relative to the foundation bed HC equals 75 m. The simulation is carried out with the length of the settling section, ledge, y equals Rn and the height equal to 0.100 m, 0.200 m, and 0.25 m. The characteristics of the settling section are determined according. The simulation results are shown in Figure 17, Figure 18, Figure 19. With the settling section y equals Rn and height equals 0.25 m, the resulting roll begins to increase sharply, θ2 equals 0.0120, and reaches the limit value set by the standards for the structure. A further increase in the roll leads to a loss of stability of the foundation slab position, therefore, the load-bearing capacity of the structure is exhausted. At the same time, the fracture lines are at the initial stage of development. Analysis of simulation results. The simulation results show that the stress-deformed state of the round foundation slab and the patterns of its load-bearing capacity, zones of formation and development of plastic hinges, under non-uniform deformation of the base surface are different from the type of change in the shape of the base surface. The main zones of formation and development of fracture lines in the slab under various deformation conditions of the base are shown in Figure 20. 1. New patterns of determination of internal forces for possible conditions of the first and second category elements of the reinforced concrete slab under complex load are established. The characteristic feature of the second category elements in the passive deformation state is the determination of the moment corresponding to the curvature of the load release curve. 2. The introduction into the calculation of the function characterizing the degree of reduction of the weakened base characteristics to determine the variable stiffness coefficient in load release allows taking into account the conditions of contact interaction of the slab and the non-uniformly deformed base. Dependences of the weakened base for collapsible soils, underworked areas, and karst areas are obtained. 3. The developed program allows taking into account the load history of elements using nonlinear diagrams in the entire range of force and deformation effects. 4. On the basis of the analysis of the obtained simulation results of slab operation on the non-uniformly deformed base under complex loads, the following conclusions can be drawn. At the curvature of the convex base surface along one axis, the maximum plastic deformation zones of the foundation structure are located on both sides of this axis, and the slab is destroyed by fracture lines formed and developed in these zones. At the curvature of the base surface, the zones of plastic deformations of the structures are located mainly in the places of reactive soil pressures concentration. The curvature of the convex base surface, and to a lesser extent the bearing capacity adversely affect the operation of the foundation slab as compared with the curvature of the concave at the same values of the vertical load Φ. Depending on the size of the settling section at the end of the foundation, the load-bearing capacity of the structure may be exhausted either due to destruction caused by the formation of plastic hinges or due to loss of position stability caused by large inadmissible rolls. The value of the limit load on the slab decreases with the increase of deformation effects of the base on it. Under non-uniform deformations of the base, the main areas of destruction of round foundation slabs are the footing support points, but in some cases, curvature of the base surface, settling of the base at the end of the foundation, such zone may occur in the central part of the slab. Thank you for the attention.